Okay, so in general, I get this transfer function. All right, so this ugly looking math thing that I put up here. All right. Now, this transfer function, what it is ultimately is it's a ratio of an output to an input. All right. So I say of an output to an input. And this would come from, something like I can define different types of transfer functions. I could say, all right, so I have V in of S here and V out of S here, right? So I could have a transfer function that was V out of S over V in of S. I have an input voltage source and output voltage that I'm measuring. I could also have a transfer function that went from V in of S to, I don't know, VR of S, right? I could have that transfer function as well. It'll have a different look to it. It'll have different poles and zeros and such, but it still has that basic look. Okay. So I already wrote here, I guess, the question I'm going to ask you, but so we defined poles and zeros, right? What is a pole? It's the value of S that causes this thing to go to infinity. All right. So when I look at this, in this particular case, I usually draw it out in this form where it's all kind of factored. All right. This is what I call my general form. I mean, in general, I could turn this into, if I have two poles down there, there'd be an S squared term and a single S term and all that sort of stuff. But I usually write it out in this form because it's really easy for us to draw the plot of this thing. Okay. So the roots of the numerator are called zeros. So I wrote that out here. So in other words, we call them zeros. Why? What's the reason? It makes that function h of s go to zero. All right, and notice that they're negative, right? And if you just solve that out, you would see why that is. All right, now what we do is we relate those to what we call the breakpoints when we draw the graph. Yeah. Now, in general, we also say we got multiple poles or zeros at the origin. I did this really generally, right? So basically what this says is that n was a positive number, I would have, let me ask you guys, if n was a positive number, let's say n was 2, okay? What would this, how many poles, how many zeros, would I have zeros or poles if n was 2? Capital N right there. Would that represent zeros or poles? Zeros, right? Because it's in the numerator then. If it was s to the minus 2, those would be poles because they would be to the minus 2s. They'd be in the downstairs, right? They'd be in the denominator. All right. We can create circuits where these things come from, right? And so for making Bode plots, I have you guys, I just give them to you. Because again, when I give you a problem on a test, I don't want you to screw up the circuit analysis, get the wrong function, and then draw the wrong Bode plot. All right. That's not fun for me to grade and you to get docked the points on. So I'll ask you to derive transfer functions. I'll ask you to draw Bode plots typically separately. Okay. All right. So what the heck is this thing? What is a Bode plot? I've used that term, right? What is a Bode plot? It's a good question, right? You guys are focused all the time on how do I get the points, but what is a Bode plot?
Well, they're logarithm plot.
It's, well, yeah. So basically what we're saying is if Vn is a sine wave at a particular frequency, I want to know what the magnitude of this transfer function is going to be at that frequency. So it tells me basically how the input transfers to the output. So if the magnitude of this thing, if I put in a sine wave that's at 10 hertz, and the magnitude of this thing is 10 at 10 hertz, then the output's going to be 10 times bigger than the input. That's what it tells us. All right. And so we often kind of use this Bode plot tool as a design thing. Okay. Now I'll back up for a second because, again, what we do is if I show something like what I showed last time, maybe I removed it here. I guess I did. This is what these graphs look like. So I did this for just a regular RC circuit. If I plotted the magnitude of the transfer function, now I'd say h of s, but this is h of j omega. What did I do here? By calling that h of j omega, what have I done? Well, I set s equal to j omega. What's that mean if I set s equal to j omega? What does that imply? It implies something.
That varies based on the.
Well, so S in general can be anything. So you guys learn Laplace transforms, and if I use Laplace transforms, you learn Laplace transforms with unit step functions and all sorts of crazy functions, right? What we're saying is in the special case where I have a sine wave as an input, S equals j omega, and this thing basically is the exact same thing as impedance analysis, and I can look at this thing to understand what the magnitude and phase change is in steady state, right? So if I plot this thing, what this is telling me is for frequencies, in this case, as I wrote it, for frequencies between 0 and 10,000 radians per second, this is what the magnitude of the transfer function is. So if I put in something that was DC, all right, what frequency is DC? 0, right? So if I put in something that was DC, my output would be equal to my input because the magnitude is 1. If I put in something here that was, I don't know, somewhere around 6,000 radians per second, the magnitude is 0.1. So my output would be 10% of my input, right? It would be made smaller by a factor of 0.1. What did I call this idea of making something smaller? Yeah, this is a low pass filter. If I make a signal out of a filter, it becomes smaller. What did I say? Attenuate it. Yeah, we attenuate the signal. So we amplify it if we make it bigger, and we attenuate it if we make it smaller. Okay. All right. So looking at this, though, this isn't so bad right now when I look at this particular filter for this RC circuit. But if I have, in this case, this thing has, looking at this, how many poles and zeros does 1 over SRC plus 1 have? 1 pole. If this thing has 2 poles, what would happen is it would fall off at a faster rate, and the graph gets really awkward to look at on this linear scale. So what we said was, instead of plotting the magnitude, right? So I did S1 over SRC plus 1. If I say, what's its magnitude? The magnitude is this thing right here, right? That's what is plotted right here. That's the magnitude of that transfer function, okay? If I plot that on a linear scale, this is what it looks like. What we do instead is we take the log of that, and what's that do when we take the log? It sort of expands the scale out. So in other words, where would 0 be on a log scale? What's the log of 0? Negative infinity, right? This guy shoots way off down there, right? Where would 1,000 be? 3, right? So basically what it does is it really expands this space a heck of a lot, right? It expands that space from 0 to 1,000, expands it from negative infinity to 3, right? So it allows me to kind of zoom in and see the action in a better way, okay? And it's, Bode is the guy who first drew these things. You can get MATLAB to draw them for you pretty easily. But where it's useful typically is for me to think through from a design perspective. Okay, like in a lot of examples that I've done, like with my company, like we were designing, instrumentation or whatever. It's like, okay, well, we say we need to minimize the signal by a certain amount in a certain frequency range. We begin with one of these plots, and then we figure out how to transfer that to a circuit. All right, how to turn that into a circuit. So it's a useful design tool. All right. So we talked through this. I don't want to go through it again, but basically what we said is if I have a single pole, all right, and I take the log of that magnitude, what we did is we said the log of that magnitude becomes this ugly looking thing, and I broke it up into 2 frequency ranges. I said for low frequencies, this guy is flat. All right. Now, the thing that's goofy that I want to talk about is I plot these things on a log scale. All right. There's also sometimes log linear scales, and you'll see those eventually at some point. Log linear scale would mean that one axis is logarithmic and one's linear. Okay. We're drawing log. So in other words, both axes are logs. Now, to make things all the more worse for you is we take the magnitude and we multiply it by 20. There's a historic reason for that. We call that a decibel. All right. Decibel is basically a unit that's used. It's a relative unit. It's used very frequently in sound, also used pretty frequently in RF sort of stuff, okay, radio frequency stuff. All right, so basically what I do is I take 20 log of that magnitude, so that becomes this whole thing, And I said, all right, I break this up into two frequency ranges. Right. I made an argument. I said for low frequencies, this guy is flat. Right. So as frequency increases, the magnitude that I drew for this would be basically sitting at 0. For high frequencies, what I said is that this guy becomes linear on a logarithmic scale. So if I think of log of omega as a variable, like x, it's like I have y equals negative 20x. And so I draw a graph that here is flat and then falls. And we say it falls at a slope of negative 20. And we give that units of negative 20 decibels every decade. All right. What's a decade? So it's basically a factor of 10 in frequency, right? So yeah, it could be the 90s or whatever, right? But it's also could be from 10 to the third to 10 to the fourth, right? That's a factor of 10 in frequency, 10 to the fourth, 10 to the fifth. We call that a decade. All right. So that's what we're looking at here. Yeah, what I did in this example is I said if tau p was 0.001, so I had this guy 1 over j omega 0.0001 like that. What I said is I'm going to use that approximation for all frequencies less than that. I'm going to call that breakpoint frequency. The breakpoint frequency here is 1 over tau p, so for 10 to the third. For everything less than 10 to the third, the magnitude is flat. For everything greater than 10 to the third, I'm going to say this guy falls at 20 dB per decade. And what I did was I showed last time, how I would make that graph. So this is how I would make the graph, both approximate-wise and then MATLAB. So the red line there is my approximate graph. The blue line is what the actual graph looks like. And I said there's a difference between the two right at the breakpoint. The reason there's a difference at the breakpoint is because the argument I made for drawing the graph like this is that I said for frequencies much, much less than 1 over tau p, and for frequencies much, much greater than 1 over tau p. So not surprisingly, the approximation is not very good for frequencies near 1 over tau p. All right, we just ignore that when we draw the graph. Okay, we sometimes call that point the 3 dB point, because what's true is that the difference is minus 3 decibels at that particular point. All right, and you could derive that it's negative 3 decibels. All right, we won't go into that. All right, now you'll notice it should make sense that I also have a graph that came out of MATLAB that shows the angle. I'm not asking you guys to worry about that in this class. You'll learn about that stuff later. It's not surprising that I would have an angle though, right? Because h of s is a complex number. So I'm plotting the magnitude of that complex number and the angle of that complex number. All right. It's the magnitude that we think about typically. Like if I'm designing an amplifier circuit or a filter circuit, I worry typically about the magnitude. I want to make things smaller in my filter, right? I don't really worry about how much phase shift there is at a particular point. You get into control systems and things like that, then you do worry about that phase, but that's beyond us at this point. Okay. All right. So in other words, this guy, we ended up last time, we said this guy's ugly. In general, that's my general form. All right. What I do is I say, if I want to plot the magnitude, I take the magnitude of this whole thing. And what I said is, if I have the magnitude of two numbers multiplied, right? Like S tau Z plus 1, S tau Z1 plus 1, S tau Z2 plus 1. Those are two numbers multiplied, right? If I take the magnitude of two numbers multiplied, I multiply their magnitudes. When I take the log of two things that are multiplied, I add them up. So what that said basically was, if I take this whole thing and take the magnitude of it and then take the log of that whole thing, all of these individual components are additive, right? So basically what it means is if I know how to approach a pole and I know how to approach a zero, I can look at each one individually and then add them up, right? So I don't have to look at the whole thing all at once. I can add them up. All right. Now, what I said was, if I'm looking at a pole, for a pole, it's flat and then it falls. What's different about the zero? The shape looks the same, right? He's flat and then he rises, right? Why does he rise? Because there's a plus sign instead of a minus sign. All right. If you did the same approximations and everything, you'd see that that's the case. All right. Now, in addition to this, there's two special cases. There's this guy here, 20 log of a constant. Now, notice one thing I do here. So when I took the magnitude of this whole thing, K is a constant. I probably give you some in the homework where K is like -10, right? -10 is not a magnitude, right? What's the magnitude of -10? 10. 10 is -10 is a complex number, which is what? If I wrote that in polar form, -10, what's -10 in polar form? 10 angle 180, right? So that guy has a 180-degree shift. So when I take his magnitude, it becomes just 10. So what's the graph of 20 log of a constant? What's that look like? 20 log of a constant, what's that? If I drew that graph versus frequency, does it change? It's flat, or it's just a line. So what I do is I look at each of these individual pieces, add them up, and then because this guy added on, I basically take the whole thing and just shift it up or shift it down based on whatever that value is. Okay. Now, what about these guys here? The poles are zeros at the origin. What's that going to do? Yeah, rise forever or fall forever, right? Because on a log scale, I think of log of omega is the x variable. So it's basically I have like y equals 20n times x. So n here is the number of poles or zeros that I have. So this is too abstract to talk about for too long. I want examples of where this starts to make sense, right? So you draw the magnitude for a pole. It's 0 for frequencies lower than the pole, falls above it. For zeros, it's flat below it, falls or rises above it. Constant K just shifts the whole graph up or down. All right. And then I have those two special cases. If I have zeros at the origin, a 0 at the origin causes the sky to rise, poles fall. Right. And you can make sense of, so on my graph here, I'm showing this as 0 on a log scale. What frequency is 0 on a log scale? What number has a log that's equal to 0? The log of what is 0? 1. The log of 1 is 0. So right here at 1 radian per second, right, this guy is crossing through here. And I can do a quick check, right? 20 log 10 of omega. If I put in 20 log 10 of omega, 20 log of 1 is what? 0. Right here. 20 log of 10. What's the log of 10? 1. Right? So here at 10, this guy's equal to 20. 20 log 10 of 100. That would be equal to 40. So I see he's right here. Right? And I could do the same math on the -20 guy. Okay. So basically, you just have to remember these basic rules and then we construct the plots. Okay. All right. So this was my process, right? This is my process. I'm not sure if iBooks looks at it this way or not, but this is the way I do it. So basically, figure out the pole and zero locations. Those are always going to be negative or 0. All right. And then what you're going to do is you determine the corresponding breakpoints, which are always going to be positive. It's going to be the frequencies. We only look at positive frequencies. So we basically say what's going to happen at those frequencies. Those breakpoints, we call them that because what's the graph do? It breaks at those points. In other words, it's flat and then it rises, or it's constant and then it falls, or whatever, right? Or it changes its slope potentially. Now, the next thing is I get the transfer function into the correct form, right? This general form. Then I generate the plot for each one. I do it moving from left to right. In other words, I move from the lowest frequencies to the highest frequencies. Okay. And then I add them up, moving left to right. So basically what I do is I add them up at each frequency and then move left to right. All right, left to right from your left to your right. Okay, I think I'm just, okay, yeah. And then I shift the whole graph up or down based on that constant. All right, that's our process. This is the example we ended on. This is the example we're going to pick up with. They had this guy, S over 10S plus 5. And where did this come from? This came from
Our
it could. This particular one, I think, came from. I'll have to think about that between now and recitation, but I think it came from that circuit. All right. With the exception of the fact that it would have had a negative sign. All right. But I think that's where I got it from. All right. Don't hold me to that. But I think that's where it came from. All right. I'll think about that between now and recitation. But it came from an op-amp circuit. Okay. S over 10 times S plus 10 to the 5th. So again, we'll follow through the process. First of all, even before I do this, is this in my standard form? No, right? Because in my standard form, I always have these guys as S times something plus 1, right? And this guy is definitely not in that form. All right. All right, so we go through our process. What are our pole and zero locations? Okay, so, all right. How many poles does he have and how many zeros does he have? One pole, 1 0. Where's the 0 and where's the pole? Yeah, the zero is at S equal to 0. It's the root of the numerator. What about the pole? Negative 10 to the 5th. Now, on a complex plane, I'm not going to probably ask you this question ever, but I always draw these things on you'll do these, it's called a pole zero diagram, and do them in controls or in systems at some point, right? We look at this graph. Now, what I care about is what are the corresponding breakpoints. All right. So if my poles are S equal negative 10 to the 5th, my 0 is at S equal to 0, I talk about my breakpoints. And what I call those in this case is the pole breakpoints and my 0 breakpoints. So the 0 breakpoint I have is basically at 0, omega equal to 0. Where's my pole breakpoint? Yeah, it's going to be at 10 to the 5th. All right. In other words, what this tells me is the graph's going to have some action at 2 places. When I say action, in other words, this is going to change its slope at those points. So it's going to have action at 0 and 10 to the 5th. On a logarithmic scale, am I ever going to see the action at 0? Where is the log of 0? Negative infinity. All right. So I'm never going to see that. Right. But it'll be there. Its effect will be there. All right. So I got to get this guy in standard form. So I said, there's my standard form. There is my transfer function. How do I get this guy into standard form? What do I got to do? Well, I got to manipulate it somehow, right? How do I manipulate it? Pull out 10 to the 5th. So I got to say, in this case, what I do is I say S over 10. Now I want to pull 10 to the 5th out of that thing. So how do I pull 10 to the 5th out? Well, I'm just going to pull it out. 10 to the 5th in front of something. How would I modify S plus 10 to the 5th and pull this 10 to the 5th out? Yeah, S over 10 to the 5th. So I'm going to say I have 10 to the minus 5 S plus 1. Right? And if I undid that, if I said, okay, multiply 10 to the 5th times this thing, you'd see that I got S plus 10 to the 5th. Okay. All right. So when I look at this, I got what looks like to me one pole at the origin, or sorry, 1 0 at the origin, right? And I have a tau P1 equal to 10 to the minus 5th. All right. And I got a K value here. What's that K value? What's the multiplier on this thing? Yeah, 1 over 10 to the 6th, or 1 over a million, or 10 to the minus 6. Like that. Okay. All right. So in my standard form, I got 10 to the minus 6 S over 10 to the minus 5 S plus 1. All right. That's what we've got. Okay. Now what I want to do is step 3. Step 3 is I got to do each of the individual guys. All right. And I went through this too fast last time, so I want to go through it slow. 10 to the minus 6 S over 10 to the minus 5s plus 1. Okay. So got one pole and 1 0. So I've got two individual things to draw on my logarithmic scale. So what I have here is 20 log. First of all, I got log paper here, right? So in other words, both the x-axis and the y-axis are logarithmic. Now, what I have here is a little chart I wrote to remind myself, all right, if omega is equal to 0.1, 1, 10, 100, 1,000, what's the log of those numbers? You should know those, right? If you don't remember them, it's not that hard. The log base 10 of 1 is 0. Log base 10 of 10 is 1. 100 is 2. 1,000, 3. So we do is on the omega axis here, right? I draw out the origin on my omega axis. I say is a frequency of 1. All right. That corresponds to 0, right? So it's the origin for me, right? Because the log of that number, the log of 1 is 0. So it sits at the origin in this graph, right? Then I say the log of 10 is 1. So that would be basically on a linear scale right there. And this is omega equal to 10. On a log scale here, this guy would be 2. So again, just breaking these out linearly, because these, in other words, these decades here are spaced. This is 0, 1, 2, 3, 4, 5, 6, 7, right? And so what I'm doing is writing out what those are and saying that each of these, this is 100, 1,000, 10,000, 100,000, 10 to the 6th, 10 to the 7th. 10 to the 7th sounds like a big number. It's not that big. What is 10 to the 7th? 10 million. So that's be 10 mega radians per second. Oftentimes we don't draw these graphs on an omega basis. We often draw them on a hertz basis. All right, because again, we tend to talk in terms of hertz rather than radians per second. All right. Now, what about the y-axis? Well, basically what we do is we label up factors of 10 again, right? So if I take 20 log of 1, what's 20 log of 1? What's the log of 1? 0. So that would be right here, right? So 20 log of 10, what's that? 20. So this guy would be 20 right here. This would be 20 log of 100 or 40. This would be 20 log of what? 20 log of 1,000 would be 60, right? And then down here, I got the negatives. Negative 20, negative 40, negative 60, negative 80, negative 100, negative 120, like that. All right. So this is step 3 of the process. Step 3 of the process is basically to draw for ourselves each individual component. So let's start. We got 2 components to worry about. Which one do you want to start with? Start with the 0. What do we do with the 0? The 0 always rises. Okay. So think of it this way. No matter whether I got a pole, no matter whether my 0 is at the origin or somewhere else, right? Zeros always rise, poles always fall. All right. So in this case, how would I draw that guy? How do I draw? Basically, what I'm drawing here, if I think about it, I'm drawing 20 log 10 of 10 to the minus 6 plus 20 log 10 of omega. That's what's coming in from the S. Minus 20 log 10 of the square root of 10 to the minus 5th omega squared plus 1. That's really what I'm drawing, right? That if I went to MATLAB and asked MATLAB, hey, MATLAB, draw me the Bode plot, MATLAB would draw that exactly. All right, now what I do is I draw each one of those separately. So 20 log 10 of omega, what's that guy do? He always rises, okay? So where would I draw him on this here set of axes? Going up. Where specifically would he go up? where's that?
From 0 to the breakpoint.
Well, so if I look at him separately, right? He basically he always goes up and he always goes through this origin. Right. Try to draw the straight line. I can. Like that. He always rises. Again, you can check this, right? If I plugged in 20 log of 1, that would be at 0. At 1 radian per second, he's at 0. If I did 20 log of 10, that would be right here. And then 20 log of 100, that would be at 40, right? You can also just remember that, right? I said the special cases I put here in the notes, right? These are the special cases. You can look at these to remember what to draw for those, okay? All right, so we keep going. This guy's done now. Let's do the next one. Let's do this guy. This is a pole. What do we say for a pole? It's flat, and then it starts to fall. So it's flat until what point? 10 to the 5th. That's my break point, right? So he's flat. In this case, I draw him out like this. Out to 10 to the 5th. And then he falls at what slope? Negative 20 dB every decade. It's going to fall like that. The next job for me here is step 4, which is to add those two things together. And then I'm going to deal with this guy by himself. All right. Now, how do I add them up? I made a statement here that when I add them up, I move from left to right, adding the results from step 3 at each frequency. So I move from left to right. So if I look at this, where's left? Well, left is all the way at the left edge. Okay, so let's start right here. At this frequency, and I'm gonna try to do is get out of this because I don't know how to do that in slide mode, but I can change my color. Try to change it. No, I don't want to go to red. I want to do black. Okay. All right. I want to move from left to right. So at this point right here, so first of all, what frequency am I at right there? What frequency would that be on the left edge of my graph? -1 on my log scale. What? Yeah, so 0.1. So if I took the log of 0.1, that would be -1. So this would be 0.1 radians per second, right? So 0.1, 1, 1, 0.1, 1, 10, there you go. 100, 1,000, 10,000, 100,000. Okay. So here at 0.1 radians per second, what's the sum of those two things? So I've got one graph is sitting at 0 and one is sitting at -20. What's the sum of 0 and -20? -20. What happens when I get to here? This guy's still 0, right? This guy here is what? Negative something. So basically what happens is I'm going to follow this line, right? Basically the whole graph is going to follow this line up until a point. At what point is it going to change? In other words, from all the way from here, all the way from -infinity up until I got to this range of action, the summation is following basically the 0. At what point is that going to change? At 10 to the 5th, right? So at 10 to the, in other words, because I'm adding 0 to this guy all the way up until 10 to the 5th. So that would be somewhere over here. All right. Now, what happens at 10 to the 5th? So yeah, what I'm doing is I'm adding at that point two graphs together. One graph is going up at 20 dB per decade. The other one's going down at 20 dB per decade. So if I added two graphs together, one that's going up, one that's going down at the same rate, what's the result of this guy going up and this guy going down at the same rate? they're going to flatten off. All right. That's generally the way that I, once you get comfortable with this, that I start to think about it. Right. This guy flattens off like that. Now, what's the value at that point? I guess I didn't give myself enough axis. So he's at 60 dB here. At 10 to the fourth, he would be at 80 dB. So he'd be at 100 dB. So this would be, if I kept this axis going, this would be 80, and this would be 100. Okay. So not done yet. What's step 5? First of all, questions about this, because it's probably the hardest part of the whole thing, is getting them added together. This notion of adding them at each individual frequency is really the thing that I always find kind of messes with people's brains. All right. You're adding them at each individual frequency. So what happens if I do now? What do I need to do to finish this? I got to do my step 5. What was step 5? Shift everything up or down based on the K value. All right, so let's look back at what I did here. Okay, so for the K value, what is the K value? Where is it? The K value is 10 to the negative 6. Okay. So what that turned into is 20 times the log of negative 10 to the negative 6. Okay. So 20 times the log base 10 of 10 to the negative 6. What's that equal to? Yeah, 20 times negative 6, or negative 120. So what do I do with that? I shift the entire graph down by 120. Okay. So as I add to everything here, negative 120. So if I add negative 120 to everything, it shifts the whole thing down by 120. So what's going to happen? What I'm going to do is I'm going to start at that break point at 10 to the 5th. Okay. Where would this point shift to if I shift it down by 120? Negative 20. So I need a new color. Purple. Go with purple. All right, so I'm going to go down here. This guy would be flat at negative 20. And then what would he do before that? He'd be rising. He'd go like this. All right. This is my graph. All right, this guy here, the purple, is for me 20 log 10 of the magnitude of h of j omega. That is it. This was the pole. This was the pole. This was the 0. This was the result of step 4, adding them all up. This guy here was the result of step 5. Okay. Now, question is, what the heck did I just draw? Right? I just drew a thing. I did a thing. Right? What's the thing? Well, the thing is the magnitude. It's what this magnitude looks like. Right? It says useful for me from a design perspective. What the heck do I do with this thing? Right? Well, let's say, for sake of argument, that let's say, so this h of s, let me go back to black. All right. Let's say I have h of s is this whole thing, s over 10 to the 5th, or 10, let me just write that, 10 to the 6th downstairs times s times 10 to the negative 5th plus 1, right? That's what this thing was. Let's say that this was built for some circuit. And again, I'll think about what the circuit is. Let's say it's V out over V in like that. Okay. All right. So it's a ratio of some input voltage to some output voltage. And so if I say to you, in this case, let's say V in was equal to I don't know, 10 cosine 10, let's say T plus, I don't know, 10 degrees plus 10 cosine 10 to the 6 T. And I asked you in this case, I could use this thing at each individual frequency and say, I want to figure out the amplitude of V out at the frequencies that are in this signal. All right. So I want to figure out what's the, first of all, if I put this signal into any circuit, right, in steady state, it's going to have two terms, right? What are the two terms going to be in there? This is an important concept, right? So if you learn nothing else, this is kind of a key takeaway, right? If I had this as the input, what's my output going to have? Two cosines. One at a frequency of 1 radian per second and one at a frequency of 10 to the 6 radians per second. Input and output always has the same frequencies, all right? The circuit may change their amplitudes and it may change their phase. That's all the circuit does in steady state, right? Is it changes amplitudes, it changes phases. So if I had this and I ask you the question, what's the amplitude of the output at 1 radian per second? How would I figure that out? How would I use this graph to figure that out? Look at 1 and multiply by the magnitude. So let's look at 1 radian per second here. All right. So the purple is our graph. So 1 radian per second. What is the magnitude at 1 radian per second? Well, where is 1 radian per second? Well, looks like it's down there at negative 120, assuming that yours truly drew it right. Let's see. Yeah, it's at negative 120. All right. So what we say here is that so be careful. 20 log magnitude of the magnitude of H of J1 is equal to negative 120. So it's negative 120 decibels. Now, the fact that it's negative doesn't mean there's a phase shift to it or something. It doesn't mean that this is a negative number or negative magnitude. What's it mean to be negative? I took the log of a number that was less than 1. In other words, if I'm below 0, I'm making things smaller. All right. So in this case, if that's not important, right, but it's just intuitively, that's what a negative means here, is that I'm making something smaller. I'm taking the log of a number less than 1. So what do I do? If I want to figure, what I want to know is I want to know what's the magnitude of H of J1. So how do I do that? What do I do to figure that out? Divide both sides by 20 and then raise both sides to the power of 10. So the first step is I have log base 10 H of J1 is equal to negative 120 divided by 20. Okay. Well, what's that? Negative 6. Okay. So what's 10 here? Or what's magnitude of H of J1? It's raised both sides to the power 10. So 10 to the negative 6. So what's my output going to be? Negative 5. 10 to the negative 5. So this guy's a good filter, right? He's getting rid of that low frequency. Now what's happening at 10 to the 6? So at 10 to the 6, I'd have to go back to the graph. 10 to the 6 should be after my breakpoint. So that's right here. What's the magnitude there? Negative 20, right? And so at 10 to the 6th, I have 20 log 10 of the magnitude of H of J 10 to the 6th is equal to negative 20. So it's still being attenuated because it's negative, but it's not being attenuated as much. So what do I do here? I say log base 10 of the magnitude of that guy is equal to negative 20 divided by 20 is what? Negative 1. Raise both sides to the power of 10, and I get the magnitude of this guy, H of J 10 to the 6th, is equal to 1/10, right? So what's my output going to be? The amplitude would be 1. So what kind of filter would this guy be? What has he done filter-wise? Is a high pass filter, right? He's making the low frequencies 0, and he's making the high frequencies a little bit less than what they were. If I don't like the fact that it's making a little bit less than what they were, this came from an op-amp circuit. I'd stick another op-amp circuit after it that had a gain of 10, and that would make it go back to the same size that it was before. Right? And the other guy, little guy, the term at 10 to the term at 1 radian per second still will be pretty tiny, right? This guy is 10 to the minus 5th volts, the output, 10 to the minus 5th volts. I don't have an oscilloscope that'll even measure that. All right. In other words, I've pretty much knocked him out and I've kept this. Okay. All right. So I'm going to stop there. We've got recitation at 2:30. I give you back the exams at that time, and we'll do probably 2 examples with my